We're getting our hands dirty today, literally. We are diving deep into the physical foundations of soil texture. In this explainer, we're focusing exclusively on the science of soil physics, zeroing in on those almost permanent physical properties of the earth beneath our feet. So let's jump right in and see exactly what makes up the ground we walk on. Here's our quick roadmap for today. First, we're going to cover the basics of soil texture, followed by the properties of individual soil separates. Then, we'll look at how to identify them out in the field with the feel method and how we do it in the lab with mechanical analysis. Finally, we'll compare their real-world properties and organize them into soil textural classes.
All right, Section 1, the basics of soil texture, defining the ground. So to start, what exactly is soil physics? Well, it's a branch of soil science that deals with the physical properties of soil, as well as measuring, predicting, and controlling the different processes happening in and through it. And right at the core of this field is soil texture. The definition here is key. Texture is the relative proportion of particles of varying sizes. We're talking specifically about sand, silt, and clay. Now here's the wild part. This texture is considered an almost permanent property of the soil. Sure, it might change incredibly slowly over massive stretches of time, but for all practical, human-scale purposes, it's fixed. Moving right along to Section 2. Properties of soil separates. Let's look at the physical fragments themselves.
Conventionally, if a particle is smaller than 2.0 millimeters in diameter, it's considered soil material. Anything bigger than that, your gravel, cobbles, and stones, just doesn't behave like soil. Now, there are two major size classification systems we use: the ISSS, which is the International Society of Soil Science, and the USDA, the United States Department of Agriculture. Just think about the sheer scale we are dealing with here. We start up at coarse sand at the 2.0 millimeter mark, and we go all the way down to clay, which both systems strictly define as being less than 0.002 millimeters. It's incredibly tiny.
Let's break down the larger two separates first. Think of sand particles as basically tiny fragments of rock, mostly made of quartz. Because of that, they're chemically inactive. They don't dissolve. They have a really low water holding capacity, meaning water just drains right through them. High percolation, zero stickiness or plasticity. Now, silt is the intermediate size. Physically and mineralogically, it's actually a lot like sand. But because silt particles are smaller, they have way more surface area. They're often coated with this strongly adherent clay, so they hold more moisture than sand and even show a little bit of mild plasticity and cohesion.
And that brings us to the big one: clay. Remember, this is the fraction smaller than 0.002 millimeters. Clay is absolutely the decisive fraction here. It has the biggest influence on how soil behaves overall. Unlike sand, which is all rounded or jagged, clay particles are actually shaped like tiny plates or needles. And they absorb water. They literally hydrate, which makes the whole soil swell up when it gets wet and shrink when it dries. If you've ever stepped in wet clay, you know. It's incredibly plastic and sticky. But when it dries out, it turns into hard, solid clods. That extreme tenacity is exactly why clay makes cultivating soil so difficult.
I absolutely love this analogy from the source material because it perfectly summarizes the whole system. It says the relatively inert sand and silt fractions can be called the soil skeleton, while the clay, by analogy, can be thought of as the flesh of the soil. It just paints such a great picture, right? Sand and silt give you this inactive structural framework for drainage, while the clay is the reactive, sticky flesh that binds it all together and reacts with the water.
Okay, Section 3, the field feel method. How do we actually identify these parts out in the wild?
So out in the field, soil surveyors use a highly practical, subjective assessment based purely on touch. It's called the feel method. It's almost like a recipe. Step 1, you take a handful of soil, add a little water, and try kneading it into a ball. If it won't form a ball at all, you've got sand. If it does, you move to Step 2. Squeeze that ball between your thumb and forefinger to try and push out a ribbon of soil. The length of that ribbon tells you a lot about the clay content. A short ribbon, under 2.5 centimeters, points to loams. A long one, over 5 centimeters, means heavy clay. You also pay attention to the texture. Sand feels gritty, silt feels super smooth, almost like talcum powder, and clay gives you that persistent, sticky cloddiness.
Section 4, laboratory mechanical analysis. Time for some rigorous precision.
Field tests are great, but sometimes you need strict scientific exactness. That's where laboratory mechanical analysis or particle size analysis comes in. It's a mandatory two-step process. Step 1 is dispersion. Before you can measure the particles, you have to break down the natural cementing agents, things like organic matter or calcium carbonate, holding them together. You do this with chemicals and mechanical agitation. Once they're totally separated, step 2 is sedimentation. This relies on Stokes' law, which measures the relative settling velocities of the particles in water. Put simply, larger particles are going to sink to the bottom faster than smaller ones of the same density.
There are two main lab methods that use Stokes' law, and it's a classic trade-off. First, you have Robinson's pipette method. This is the gold standard. It's highly accurate and involves pulling exact volumes of suspension from specific depths at specific times. The downside? It is incredibly time-consuming. On the flip side, we have the Bujoko's hydrometer method. This uses a calibrated hydrometer to measure the continuous decrease in the density of the soil suspension as things settle out. It's way faster, great for running a lot of samples, but it's inherently less accurate than the pipette method.
All right, Section 5, Comparing Soil Properties. Let's see how these mixtures behave in the real world.
Because ultimately, the texture dictates the behavior. Just look at the extremes here. Sand gives you excessive internal drainage and very low plant available water, but the tillability, how easy it is to work the soil, is great. Contrast that directly with clay. Clay has massive plant available water, but its internal drainage is fair to poor. And, as we talked about with its stickiness, tilling it is categorized straight up as difficult. Sitting right in the Goldilocks zone in the middle, we have our loams and silt loams, which balance everything out to give you good drainage and solid water availability.
And that brings us to Section 6, Soil Textural Classes. Let's officially categorize these mixtures.
Based on their exact proportions, we divide soils into 3 fundamental textural groups. First are the sands, which are soils where sand makes up 70% or more of the weight. Then you have clays. Now this is fascinating. It actually only takes at least 35% clay separate to completely dominate the soil's behavior and classify it as a clay. And finally, loams. An ideal loam is a perfectly balanced mix of sand, silt, and clay that exhibits equal parts of those light and heavy properties.
To figure out the exact classification, soil scientists use this brilliant tool, the ISS soil textural diagram. It's basically a giant triangle, where each side represents the percentage of one of our separates, sand, silt, or clay. Once you have your exact lab numbers, you just trace the lines inward from each side. Where those 3 lines cross inside the triangle, that is your highly specific textural class. It might be a sandy clay loam, a silt loam, or straight clay. It's just a perfectly structured visual map of a soil's physical identity. So, we've walked through the definitions, the lab tests, and the real-world realities of sand, silt, and clay, and I want to leave you with this to chew on. If soil texture really is an almost permanent physical property, how does the precise ratio of that inert skeleton to that reactive flesh fundamentally dictate the agricultural potential of the land directly beneath your feet? It kind of makes you look at the ground differently, doesn't it? Thanks so much for hanging out with me for this explainer. Keep digging into the science, and I'll catch you next time.